Diagram of carbon monoxide CO. It is a heteroatomic molecule having the two types of atoms, carbon and oxygen, which are forming the bond. So we will explain it on the basis of molecular orbital theory. So while drawing the molecular orbital diagram of CO, we will consider the atomic orbitals combining to form bonding and anti-bonding molecular orbitals. Carbon having electronic configuration 1s to 2s to 2p2, and oxygen has 1s to 2s to 2p4. These two there are atomic orbitals 2s of carbon and 2s of oxygen combining together to form the sigma 2s and sigma star 2s, that is bonding and anti-bonding molecular orbitals. Similarly, 2p and 2p will combine to form sigma 2p and pi 2p, sigma 2pz, which we will consider along the internuclear axis, and pi 2py and pi 2px along the perpendicular to the internuclear axis. Now for carbon and oxygen, we are showing the 2s energy levels. It is somewhat higher in case of carbon and lower in case of oxygen because they are two different atoms having different electronegativities and different sizes. Both of them are having 2 electrons each, and they are combining to form the bonding molecular orbital sigma 2s. Sigma C2s O2s. This is bonding molecular orbital. Similarly, and it is having 2 electrons. This is the molecular orbital formed by the combination of the atomic orbitals. Then the anti-bonding molecular orbital formed by the subtraction of atomic orbitals of carbon and oxygen, that is 2s and 2s of both of these, to form the anti-bonding molecular orbital that is represented as sigma star C2s O2s. Also having 2 electrons. These electrons present in the atomic orbitals are distributed in the molecular orbitals. There will be 2p orbital of oxygen, somewhat raised in energy level, but they are of equivalent energy. So 2pz of the p orbital, which is along the internuclear axis, gets somewhat intermixing, gets involved in some intermixing with the 2s orbital, and there is sp mixing occurs. So we will show the 2p orbital of oxygen as 2px, 2py, and 2pz. Having 4 electrons, 1, 2, 3, and 4. Now this 2pz and 2s orbitals of the oxygen get intermixed together. Now we'll draw the 2p orbital of carbon also, which is somewhat higher in energy level. So px, py, and pz. We are having 2 electrons. Now sp intermixing takes place. And in this way, sigma star C2s O2s acquires some bonding character or some p character due to the intermixing of the s and p orbitals in case of oxygen. And this is the p character introduced in the anti-bonding molecular orbital of the s type. The character in the sigma C2s sigma star C2s O2s. That is the bonding character is introduced. Now this 2px and 2py of carbon and 2px 2py of oxygen. They are forming pi 2py orbitals, which are two pair of orbitals. They are degenerate, having the same energy, and these are the bonding molecular orbitals. Pi to P. This 2s and 2pz of the carbon also, they get involved in some sort of intermixing. This is called sp mixing of the orbitals of the same atom, and hence some anti-bonding character is introduced into the bonding molecular orbital sigma 2p, and hence it is raised in energy level. So pi 2py is lower in energy level as compared to sigma 2p due to sp intermixing, and the sp intermixing is more pronounced in case of carbon monoxide, as there is a difference in electronegativities of the two atoms, carbon and oxygen. So this is pi 2p. This is sigma C2p O2p. Sigma C2p O2p becomes the highest occupied molecular orbital. This is the orbital which is highest in energy level, which is occupied. Due to the S character in the bonding molecular orbital. S character in sigma C2p O2p, which is the anti-bonding character. That is why it is raised in energy level as compared to pi 2p, and it becomes the highest occupied molecular orbital in case of carbon monoxide. HONO, highest occupied molecular orbital. Now the anti-bonding molecular orbitals are also formed, that is pi star 2p and sigma star 2p. The pi star 2p are the two degenerate molecular orbitals, anti-bonding in nature, and this is the lowest unoccupied molecular orbital. It is the lowest molecular orbital which is unoccupied, because all the electrons are now filled and pi star 2p remains empty. So it is lowest unoccupied molecular orbital. And above that is the sigma star 2p orbital. That is also the anti-bonding molecular orbital. Sigma star 50. Sigma star C2P O2P. This is the molecular orbital diagram of carbon monoxide, and this is the diamagnetic molecule for which the bond order can be calculated. The bond order is equal to half of Nb minus Na, where Nb is the number of electrons present in the bonding molecular orbital and Na is the number of electrons present in anti-bonding molecular orbital. So sp mixing occurs when sp mixing refers to the interaction between the 2s and 2p orbitals, atomic orbitals. Orbitals which can alter the energy levels. Energy levels and the shape of the resulting molecular orbital. So the energy levels are also altered and the shapes of the resulting molecular orbitals is also changed due to the sp mixing. In carbon monoxide CO, the difference in the electronegativities of carbon and oxygen difference in electronegativities between carbon and oxygen leads to the strong sp mixing. If the more is the electronegativity difference between the two atoms, more is the sp mixing. This mixing is more pronounced. More pronounced for the sigma orbitals. Resulting in a change in their relative energies. Now, bond order can be calculated by counting the electrons present in bonding molecular orbital and anti-bonding molecular orbitals. And that is Nb minus Na, half of Nb minus Na, that is equal to Nb is 8 and Na is 2. So half of 8 minus 2, that is 6 by 2. Bonding orbitals have 8 electrons and antibonding have 2. So half of 6, that is equal to 3. So there is a triple bond between the nitrogen and oxygen, because whatever is the bond order, that gives an number of bonds present in the molecule. And it is also diatomic, and it is diamagnetic also, because all the electrons are paired, as we can see in the molecular orbital diagram. That no unpaired electron is present in here. So it is a diamagnetic. Okay. sp mixing. sp mixing brings p character in into the sigma C2S O2S molecular orbital, making it even more stable. Here we will write sigma star because it is anti-bonding molecular orbital in which the p character is introduced, and that makes it more stable. The bonding character is introduced into the anti-bonding molecular orbital, sigma star C2SO2S. Sigma C2P O2P, it acquires anti-bonding character. Anti-bonding character, making it slightly anti-bonding. So the bonding orbital acquires anti-bonding character and the anti-bonding acquires bonding character. The highest occupied molecular orbital is sigma C 2p O2p, because the anti-bonding character is introduced in this molecular orbital by the 2s orbital of carbon. and sp mixing 2s and 2p of carbon, they get intermixed together. Actually 2pz of the p orbitals and s2s orbital of it shifts to a higher energy level. So it becomes highest occupied molecular orbital. So here in the case of carbon monoxide, sigma C 2p O2p lies above the uh, pi 2p bonding orbitals. The lowest unoccupied molecular orbital is the doubly degenerate pi star pi star 2p orbitals. Now this is all about the molecular orbital diagram of carbon monoxide. Now it will be clear how the energy levels get modified by the sp mixing. Now we will draw the molecular orbital diagram of nitric oxide, that is NO. Nitrogen has electronic configuration 1s2, 2s2, 2p3, and oxygen 1s2, 2s2, 2p4. We show the atomic orbitals of nitrogen and oxygen. 2s and 2p. 2s is somewhat higher in energy level in case of nitrogen than in case of oxygen. Both are having 2 electrons each. And they are forming sigma 2s and sigma star 2s, that is the bonding molecular orbital and anti-bonding molecular orbital, while they are combining. Now atomic orbitals form the molecular orbital. It is the bonding molecular orbital, sigma. It's having 2 electrons. This is sigma n 2s O2s. Then anti-bonding molecular orbital sigma star and 2s O2s, which is also having 2 electrons. Now the 2p orbital in case of oxygen, it lies above the 2s, having px, py, and pz orbitals, of which the 2pz orbital, which is along the internuclear axis, it mixes with the 2s orbital of oxygen. So sp interaction takes place here, and in that manner, bonding character or the p character is introduced in the anti-bonding sigma 2s molecular orbital. And it is somewhat lower in energy and more stable also. Now 2p of nitrogen and 2p of orbital of oxygen. they will combine to form sigma N2P O2P. And in the sigma combination, there is a 2s orbital of nitrogen is also involved. Actually, the 2s of nitrogen and 2pz of nitrogen, they get involved in sp intermixing. And so due to sp interaction, orbitals is modified, and then it combines with the 2pz of oxygen to form the bonding molecular orbital. Okay. 2p of nitrogen combines with 2s of nitrogen. This is called sp interaction. And in that manner, 2s is involved in sigma N2P, sigma N2P O2P bonding molecular orbital. And in that, some anti-bonding character is introduced, but that is not that much pronounced in case of nitric oxide, as the electronegativity differences in nitrogen and oxygen are not much, as was in case of carbon monoxide. So this orbital remains in lower energy level. Sigma N2P, O2P, and pi 2P is somewhat higher in energy level as compared to this. Pi 2P xn, pi 2Py, and sigma 2P, each are having 2 electrons each. So now 1 electron is left, which will be filled in the anti-bonding molecular orbital pi star 2P, which are pair of orbitals which are degenerate, and one of it has 1 electron. So that becomes the highest occupied molecular orbital, sigma star 2P. So sigma star 2P also, which is highest in the energy values shown above the pi star 2P. That is the sigma star 2P, formed by the combination of 2pz and 2pz of N and O. This is sigma star 2P. And it is empty. It is the lowest molecular orbital which is unoccupied. So it is LUMO. So here we can see that sp interaction is also playing its role, not so pronounced in case of NO as it was in case of CO, due to the electronegativity differences between the atoms involved in the formation of molecules. So in nitric oxide, there is weaker sp mixing and a different number of valence electrons also. That results in the bond orders of 2.5. And a paramagnetic corrector. Here we can see that 1 electron is unpaired. So it has acquired the paramagnetic character. Bond order we can calculate by using the formula half of Nb minus Na. Number of electrons in bonding molecular orbitals is 8, and the number of electrons in anti-molecular orbitals is 3. So half of 8 minus 3, that is 5 by 2, and it is 2.5.